Hello and welcome back to the Jamsey Online YouTube channel. Today we're going to be balancing the rotating assembly for the 396 big block Chevy that we have in the shop. If you're new here, be sure to hit that subscribe button and let's jump right into it. This build is going back together basically stock with the exception of a few upgrades, but our philosophy is that we put the same level of care into every engine we build, regardless of the application. We're starting here with getting our set of Speed Pro forged pistons weighed out. And out of the box, a set like this will generally be within a few grams, but with just a little bit of work, we can get them to within about a gram of each other. To begin with, we're actually going to weigh out each piston and each piston pin individually, taking note of all of the weights. By simply pairing up the lightest pins with the heaviest pistons, and the heaviest pins with the lightest pistons, we can bring our overall discrepancy to within 2 grams. At 2 grams out, we've arguably already met the point of diminishing returns, but a bit of strategic weight removal on a few of the heaviest pistons will bring us down to a discrepancy of less than a gram, which is what I like to shoot for. Once the pistons and pins are all within about a gram, we're going to move on to getting the connecting rods balanced, which is a bit more complicated. Also, by the way, if you missed last week's video on resizing this set of rods with ARP bolts, be sure to check it out after you finish this video. While having the pistons match based on the overall weight is sufficient, you can't simply make the overall weight of each connecting rod match. Instead, we start by weighing only the big end of each connecting rod with the fixture that you see here. Later on, when we calculate our bob weights, the big end of the rod is considered rotating weight because it's directly mated to the crankshaft and rotates inside the engine, while the piston and the small end of the connecting rod are considered reciprocating weight since they do not rotate but rather reciprocate up and down in the cylinder. With all of the big ends weighed, we'll head over to the grinder and carefully remove material from the balance pad on each of the heaviest rods until we're within that 1 gram tolerance that we've set for ourselves. It's probably unnecessary, but I also take a quick second to polish the area that we've ground on once we're within spec. Since we know the big ends are within tolerance, the next step is to take the overall weight of each connecting rod and then move back over to the grinder and remove the required amount of material from the small end balance pad in order to make the overall weight match. Okay, so I'm going to go through here and one last time record big end size, our small end size, and our total weight size. You could just do big end and total weight. I like to throw the small end on here and double check. I can imagine there might be a lot of people wondering at this point, why spend the time and energy to balance the rotating assembly in anything that isn't a race car? It doesn't take a genius to understand why balancing is important in a race engine, where every 0.5% of power and efficiency matter, not to mention the simple fact that race engines operate at much higher RPMs, which multiplies the forces resulting from an imbalance in the rotating assembly. But is it really going to be worth it in a street engine? Well, it may not be necessary, but the benefits are still there. First and foremost, a balanced rotating assembly reduces vibrations and gives a smooth running engine that is pleasant to drive. Reduced vibrations also mean less wear and tear on motor mounts and external accessories. A properly balanced rotating assembly also reduces the internal loads resulting from imbalance and thus reduces wear and tear on the internal components like the bearings and the crankshaft itself. Even such, there can still be countless uncertainties inside the engine even with a quote perfectly balanced crankshaft, such as the fact that inside the engine varying amounts of oil will be clinging to and slinging from the crankshaft, thus producing imbalance regardless of how close to perfect your crank is according to the machine. For us, it comes down to using the tools available to us to produce the best running engine possible. We've got our rods balanced, we've got our pistons balanced, we've weighed everything out, and now we're going to build our bob weight card. So piston weight, we have an average of 875 grams. Pin weight, I just include the pin with the piston weight. Together, we have an average of 875 grams. Piston rings, we're at 59 grams per set. Pin locks, we don't have any pin locks because these are going to be press fit on the pistons. Stroke rail, we don't have that. Total rod weight came out to an average of 824 grams, 0.3. Big end weight of the rod came out to an average of 585.1. The bearing insert came out to be 62.2 grams per rod. On the crankshaft, we have 2 connecting rods on each journal. We do a reciprocating factor of 50% on a big block Chevy like this, on a 396. Oil allowance, I'm going to put 4 grams in. So this little calculator here spits out what our totals are for everything. For the bob weight, We're sitting at 2,471.8 grams, and 50% of that for each half of the bob weight is 1235.9. So that's the number that we're going to be making each half of our bob weights weigh. This is one of our bob weights that we use to simulate the entire rotating assembly on the crankshaft when we're balancing it. One thing I don't really like about it is that all we have to make our weight up are these little discs. You can only get within about 5 grams with these discs before you have to start either cutting them like the last guy did, or finding something little to make up just 5 grams or 2 grams or 1 gram and so on. So I end up wasting quite a bit of time actually setting up our bob weights because we don't have a consistent weight. I went ahead and bought a sheet of brass that's about 60 thousandths thick and 2 sheets of aluminum that are about 30 thousandths thick. And I'm going to cut some different weight discs here so that we can hopefully lean out that process a little bit and make it more quick. So something I did this morning is set up a little calculator here on Google Sheets, and basically what I did is I measured the width and the length of both of these sheets, and then I measured the thickness of both of the sheets, or all 3 of the sheets, and then I weighed all of the sheets, and I set up on here a calculator that basically takes into account all of those different factors and spits out what the density of this sheet is. So for the brass, we got about 8.52 grams per centimeter cubed, and on the density for the aluminum, we have 2.75 grams per centimeter cubed. At that point, I can take those values and put them into another calculator here, and basically what we're going to do is we're going to make discs that are just like this with the center hole, but instead we want to find out what diameter we need on the outside to match up to the specific weight that I want. So I'm going to cut some 10 gram weights out of the brass, some 5 gram weights out of the brass, and then I'm going to cut some 1 gram weights out of the aluminum. So for the 10 gram weights, we need a diameter of 3.26 centimeters. For the 5 gram weights, we need a diameter of 2.35 centimeters. And for the aluminum, we need a diameter of 2.49 centimeters. We're going to make sure we have abrasive in the water jet, get our material in place and the nozzle height set, and with our program loaded for the 10 gram and 5 gram weights, we can get it running. A project like this is a perfect example of why we decided to partner with Wazer, because a small footprint water jet like this is perfect for a shop like ours that doesn't have enough space or enough demand to invest in an industrial sized water jet, but the Wazer is sure nice to have when you want to cut materials like this with CNC precision.
What are you doing?
I'm making you some round tuits. Actually, here's one. Why don't you go do some of those jobs that you've been telling me you'll do when you get around to it? Employees, am I right? Anyway, as the water jet cuts out each disc, a small tab is left on both the ID as well as the OD, such that once the pieces are cut, they're not blasted around inside the machine due to the water pressure. The tabs are small, so it's easy to break them loose and break out the centerpiece as well. I know I could have been more efficient with my material, but this was my first go of cutting brass, as well as the thinnest material that I've cut yet, so I wasn't sure how flimsy it would get. The tabs do leave a tiny burr, but the inside hole was easy to clean up with a 1/4 inch drill bit, and the outside tab was easily filed off, and I also used a file to quickly deburr each weight. I was pretty impressed because all of my weights came out to be nearly perfect within a small margin of error, which I attributed to my somewhat crude calculations. The result is a streamlined process for setting up our bob weights, allowing me to be much more precise in setting the bob weights to a much tighter tolerance from our calculated weight, and while it may have taken me an extra hour or two today, I can guarantee it will save me days of work over the coming years. With the bob weights built, we're finally ready to move over to the Sunnen DCB 750 crankshaft balancing machine to get it set up to spin the crank and measure the imbalance. With the crank mounted, we'll position the first throw at top dead center and mount the first bob weight level. And yes, I use the level on my phone for this. The rotary encoder on the machine reads the index of the crankshaft as we rotate, allowing us to rotate in exactly 90-degree increments to mount each bob weight level at 90 degrees to each other. I should note that this crankshaft has already been ground, but it still needs to be polished. everything's dialed in here on the balancer. Bob weights are set up. Hit start. So now it's going to spin up to 500 RPM, and it'll do a really quick check to see if it's way out of balance. If it's way out of balance, it doesn't spin on up to the high speed. But there it goes. We're pretty close apparently, so it spun on up to 750 RPM. Actually, it's pushing 800 here right now, trying to dial in how fast the motor needs to spin to maintain a steady RPM. And now it's measuring, counting down here over here on the screen. And so it's telling us we're 2.3 grams out on the left side here, 8.3 grams on the right side here. Because what I've done on the setup here on the machine, you tell it how far apart the stanchions are, you tell it the diameter of the main journal here for how fast it needs to spin, you tell it how far in the counterweight is that you're going to be removing or adding weight to. So on this side, you know, we measure from the center here to here, and the center here to the center of this counterweight for, you know, the front and back side. And the other thing you do is you tell it what the radius basically is to the outside of the counterweight here. And that way it knows, okay, you know, this much force means you need to remove this many grams out here. Because as it's spinning, it's keeping track of the forces as this thing spins around. So we're 2.3 grams over here, 8.3 grams over here, so pretty close already, but we can definitely get closer. And we actually need to remove weight. Our 8.3 grams needs removed right about there. And we're going to start with that because when you change the heavy side, it can change the light side. But right now it's also saying 2.3 grams about where this hole from the factory is. So pretty close there. Right now I have it programmed in here for a 17/32 drill bit, which I'm going to be using. And with that programmed in, it says we need to drill 300 thousandths deep right square in the center here. Just kidding. Apparently my microphone ran out of juice here, so we're going old school with a silent film. Since our balancer isn't set up with a built-in drill press right now, we've moved over to the TCM25 and set up to drill our hole 300 thousandths deep, just like the machine told us, but I'm also using a magnet to catch the cuttings, which I can then weigh to double check myself as I go. I couldn't catch them all, so once we hit 7 grams, I decided that we should head back over to the balancing machine and spin it up to see how we were doing. Since the audio is gone, I suppose I could just make up anything I want, but as I recall, we were within a gram on the right side here at this point, and maybe still 2 or so on the left-hand side. The balancer was telling me to remove weight on the left side exactly at the location the factory had removed weight, so I found the same size drill bit, which the machine told me could be used to drill about 30 thousandths deeper and achieve the right amount of material removal. 0.8 grams. Let's see where. Turns out I could have gone slightly deeper, but at 0.8 grams on the left and 0.3 grams on the right, we're going to quit chasing it because we finally satisfied the perfectionist in me. However, I did decide to do an experiment, so I grabbed a dollar bill and shoved it inside the hole in the left counterweight, taped over it, and spun up the crank. Okay, so that dollar bill and a little bit of tape on there. Now we're 2.1 grams on the left side here. Let's take the dollar bill out. We'll spin it again. And there, we're back to 0.7 grams. Just shows you how insignificant a gram is. I mean, it's like if you took a dollar bill and taped it right here. In fact, there's that dollar bill and the tape I used. 1.5, 1.4 grams, somewhere in there. And you add that to the 1.4 right there. Add that to the 0.7 that we spun, and you have it. I guess what I was trying to say is that at this point we have quite literally reached the point of diminishing returns that I keep mentioning. We could surely try and chase that last 0.8 grams all the way down to 0, but the chances of it meaning anything in regards to the performance and reliability of the engine are literally 0. From here, we're going to go ahead and get the bob weights removed from the crankshaft. Before the crank is ready to be installed in the engine, it's going to get the final polish as well as cleaned and checked. I want to say a big thanks if you stuck around till the end of the video. Be sure to like and drop a comment for my dad and I to read, hit that subscribe button, and we'll see you in the next one.